Hello and welcome back, everyone. What I want to do is I want to finish the proof for the equation that the acceleration of an object traveling around in a circle, that the magnitude of that acceleration is the square of the speed divided by the radius of the circle. So let's do that. Just get my computer ready here. Okay, let's go back. Here we are. Okay, now I've already drawn a few pictures here. If you remember from the first part, we had an object. In this case, it amounts to two black dots. Excuse me, let me get this set up again. Let's use black. Okay, so we've got two, I'm going to call them black dots, traveling around this circular path. This could be a runner going around a circular track, or an airplane banked in a turn going around a circular path. And we have it at some initial velocity and some future velocity. And you can see that the direction of that velocity has changed because the velocity is always tangential to this circle. And one thing, I can't remember if I mentioned it in the last slide or not, but we're going to look at the condition where the magnitudes of those velocities are equal. So we have constant velocity all the way around. Now what I've done over here is I've looked at those velocity vectors and I've broken them. I want to break them up into components. And notice that this angle here is this angle here, and same deal over here. Because with this black dot, this runner or airplane or whatever, I'm going to look at them where the velocity is at a certain angle below the x-axis and then the same angle above the x-axis. And here's the definition of acceleration. Now we're going to look at the x component. If we look here, notice that here are the x components. This would be v final x, and this is v initial x. Notice that this one is in the negative direction, and this is in the positive direction. And you can kind of see that over here. And over here, this one up here has a negative x component. So when I do this, let's write it down. Ax is equal to delta Vx over delta t is going to equal, again, it's going to equal V final x minus V initial x over delta t. And I'm going to talk a bit more about delta t, but clearly delta t is the time for the object to go from here to here. That's delta t. It takes that amount of time. And we're going to come back to that. So look what we have. Notice that if I just kind of write here, V initial x, he has to equal the magnitude of that velocity sine of that angle. And V final x has to equal, and it's going to be negative, V initial, or V final, and actually, let me scratch that. Let me write it over here so I don't get it all squished up. V final sine of the angle. Again, this is the sine part. Here's the angle. There's the magnitude along here, and that is the sine component. So we have this, little squished. I guess that's my style. So V final is going to be minus V final magnitude sine theta minus VI initial sine theta divided by delta t. Now remember what I said up here, that V final and V initial, their magnitudes are equal. So these guys are equal. Everything in those parallel lines. So I can then write, basically, let's just put a V here, sine theta, subtract V sine theta over delta t, which if you look, that's just 2 V sine theta over delta t. So that's a big step. Let's go to the next page. So we have established that AX is equal to minus 2V sine theta over delta t. Now right now it doesn't look very promising. We're actually looking for an equation here that has 2 V's into it divided by an R. What we're looking for does not have time in it. Now there's one thing I want you to do is, or I want you to think about that circle again. And let me just draw it fairly quickly here. This is theta, and this is theta. Notice this is a physical circle. It has a certain arc length that we can call S. Now, in general, and this is something you might want to review a bit of your math over. If this is the arc of a circle, part of a circle, sort of a piece of a pie, and this is radius, then there's a relationship that S equals R theta. That if you know this angle in radians and the radius of this piece of pie, you can figure out how long the crust part is. So we can do that here. We can say that this S must equal R. And again, my object is going around a circle of radius R. I've mentioned it, but I haven't drawn it in before, but that's radius R. And it travels through, in this case, this S here goes through 2 theta. Now one thing to notice that speed, which let me just call the magnitude of the velocity, he's a distance over a time. And remember how I mentioned on the last slide that it takes a certain time t to go this distance. That's what the t is that you see right over here. So we can actually write this magnitude of this speed, the magnitude of the velocity, which is the speed. The distance is this s over that time, which is, let's call it 2r theta, just rearranged this guy, all over delta t. And notice that is nothing more than what I'm calling big V in this equation right up here, because that is just the speed of this particle going around. And I've established it in terms of, over here, in terms of the time and the actual distance traveled. What I can do is I can use this statement here to eliminate that nasty looking delta t business. So I can say that delta t is equal to 2r theta all over v. And what I want to do is, again, this guy is this. So I'm going to put this in for that. And let me do it just over here. So AX is equal to minus 2V sine theta all over 2R theta divided by V, which equals, this V on the bottom actually flips all the way around to the top. And notice this 2 will cancel with that 2. So we're left with this. We're left with V sine theta. And then there's this V here. Came up here, as I mentioned. That's this guy. Divided by r theta, which I can then write as minus V squared, because they're the same V's, all over r sine theta all over theta. So let me go to the next page and write that a little bigger, a little clearer. I think I gotta establish my pen again. So we have discovered that AX is equal to minus V squared over R sine theta over theta. And again, just to quickly draw my circle again, as best I can. Here we are. We are looking at, this is the X, so we're trying to figure out the acceleration in the X direction as this guy goes from here to here over some time delta t. And look what we have. Now something I would like to do is, this is essentially an average velocity over delta t. What would be, what is the instantaneous acceleration? Which basically means, what if we limit, what if we take delta t and get it really close to 0? What that means is we're going to actually look at it where we make these angles really small. Notice if theta gets smaller and smaller, then our time to go from here to here lessens. From here to here. So you can essentially look at a circle. And we want to look at the object from here to here. So we're going from here to here. We have a really, in here is the little theta. And in here is a little theta. And this becomes, that's delta t approaching 0. And that works basically as our thetas approach 0. If that makes sense. This is some of the limit business that you would have seen in calculus. So look at this equation again. Delta x equals minus v squared over r sine theta over theta. What does that approach as theta gets really small, which approaches 0? Well, one thing you can recognize, and you may have seen this, you may not. If you haven't, you should convince yourself that it's true, and you can actually do this by putting in values. But one thing that's true is that as theta gets small, then sine of theta approaches theta. And if you put these angles in radians, you can see that it's true. Take 1 degree, convert it to radians, and that will give you this. Then put 1 degree in here and take the sine of it, and you'll see that you'll get very close to 1 degree expressed in radians. Again, you have to take 1 degree, express it as radians, and then you have that number. Then you can take 1 degree or 1 radian, depending on what your calculator is set at. Take the sine of it, and you'll see they're equal. What that means, again, if I go back, actually, I need a new slide, just a second. Let's keep that. Let's go to, let's insert a new slide, and maybe another new one, and go back. And here we are, so we have AX is equal to minus V squared over R sine theta over theta. If we now sort of take the limit as theta approaches 0, we know that sine theta approaches theta. So we can write that AX is equal to minus V squared over R theta over theta, because this guy approaches just theta. Now you might think, why not throw 0 in there? And that actually gets you into a little bit of trouble. You just want to recognize that as you approach 0, you're not 0, but you approach 0, these guys have the same meaning. Recognizing this is quite useful in physics. And these cancel, and you are left with AX, and we'll call this the instantaneous, is equal to minus V squared over R. And notice, I could have chosen to do this with I could look at the particle as it rounded the y-axis, or any part of that circle. So this is true in all places. So it means, if I draw a circle for maybe the 10th time, that as a particle goes around, it has an acceleration pointed towards the center. That's how it works. And the magnitude of that acceleration, its size, is proportional to the speed, so how fast you're going around, divided by the radius of that circle. And that's a neat little formula. I think Sir Isaac Newton may have come up with that. He certainly used it. We're going to use it a couple of times. So anyhow, I hope that made a little bit of sense. And we're going to talk about it a bit more in class, I think, tomorrow. So that's all for now.